right, here we go. The last lecture, video 2. I have to break it into parts. Again, somewhat complex, so we don't want to be rushing through this. So let's go ahead and take a look, see what we got going on here. All right, so this is, actually I'll go back one slide. And this is where we left off, this nice summary of what it means when you change the concentrations, or you change this cell from the standard conditions. All right, if you would increase the cell potential versus decreasing the cell potential, and knowing those different things. Now, in this portion of the lecture, we're going to talk about concentrations. And you can see that the zinc has deviated from the 1.0 molar concentration that it is under standard conditions. All right, so you've got this nice reaction. It's already balanced here for you. Shows the molar ratios. So you want to find the change in gold. What you can do is you can actually essentially start with the 0.14 moles that it increased. Okay, so it increased 0.14 from the 1, and then you do a little, because you're going to want molarity at the end, you're going to do this fancy little conversion here. So this is really brand new. You haven't quite done this. You know, you're not really starting with a number over here. So you're using a conversion in the first step. And then your mole to mole ratio. This is a type of stoichiometry problem that we have not done. But what it tells us is it allows us to look at that small increase in zinc and then put it in perspective to see what would then be the change in gold, relatively speaking. Okay, so it's sort of that give and take thing on both sides. So this one increased by a factor. So what would the decrease be for the gold? Now notice it's moles per liter, and it's now moles of gold per liter, which is molarity. So you have 0.093 molar. Important to remember that you're starting at 1. Really let this number drive the sig figs, because this is pretty much you know, as many sig figs as you need. So since this was 3 places to the right, use 1 at 3 places to the right, and then 0.907 would be the corresponding concentration of gold if the zinc had gone up by this factor. So this is a good kind of problem. I would circle this whole thing, and this would be a good one to look over in reviewing for the AP exam, because this one takes some real thought. That problem's not going to jump out at you. You notice when we do problems that are brand new, we jump right to the answer, because I would not have expected you guys to come up with this answer without seeing sort of the strategy of a problem like this. So you can write thinker, or a tough one over in the margarines of your notes, or the butter of your notes, whichever one works better. Okay, so we're almost to this is the penultimate equation on the purple sheet. There's one more that we'll talk about tomorrow, but this is the Nernst equation. And you look at this and you go, E equals E, what's going on there? Well, the circle, we all know, means that it's at standard conditions. So what E represents in the Nernst equation is you can compensate the number of the standard condition by using this relationship. Okay, so if you wanted to look at the EMF under non-standard conditions and actually calculate that, well, you're going to use R in the Joule mode, temperature in Kelvin, moles of electrons transferred. That should sound familiar. And then we're going to throw in Faraday's constant as well. And this, as you can see, takes into account, we showed the relationship of equilibrium to the E0. So having that in there is an important part of showing the relationship, because if you know what the equilibrium constant is at that given moment, or Q, that will allow you to say, how it's related to the what it would be under standard conditions. Okay, so that's on your purple sheet. So you do have reference to that, as well as definitions of what these letters stand for. So really, again, study that purple sheet. Okay, so here we have a simple little equation. A plus B gives you C. C on the top, A, B on the bottom. Now, we want to look at this in terms of just a quick understanding of doing this without actually crunching any really big numbers. So let's say you knew this, that Q was less than 1. Okay? Now we know from the equilibrium constant that that means that there's a lot of A and B. Okay? Big number, small number, that's less than 1. Now what that does to your natural log of Q is that makes that negative. Now notice it's already negative. So if this number is negative and you're multiplying them, negative times a negative is a positive. So your E0 then would increase by this factor, making E greater than E0. And you see how we did that without really crunching any numbers. And if Q is big, that means a lot of products, a lot of C. That would make the natural log positive. Okay? And meaning that you're going to now subtract something from E0, and E will be smaller than E0. So this is a real nice page here. Circle the bottom half of this for reference of a quick answer, like in a multiple choice format. Very, very likely you'll see something like that as an application to the Nernst equation. Okay, so here we got an interesting question. So you got this nickel with solid chromium giving you solid nickel and chromium plus 3 ions. Okay, so would the voltage of a cell that operates according to standard conditions be greater than, less than, or equal to that of a cell? So this first one is a standard cell, and the second one is the nickel plus 2 is going to decrease. See, it's going to be less than 1. And the chromium is going to increase and be greater than 1. All right? So in a standard condition, that would be 1. So this guy went down. At standard conditions, this would be 1, and it goes up. Okay? And it increases. Now, they're going to talk about this as a possible answer. But I'm hoping that you can go, hey, Le Chatelier's principle says that if you add more here, and take away there, that's going to drive this thing to the left, which is going to slow your battery down. We did talk about that. All the way back right here, a summary where you would have decreasing the cell potential, okay? Because Q is going to be greater than 1 because you got more going on the right side. So you could use that to answer it. Also, you could use the Nernst equation. So this sort of gives you a second method of figuring this out. So if you look at it, more products than reactants would give you a positive value for Q. And if this is positive, that's going to make E0 smaller, and E would be less than E0 according to the Nernst equation. So if you were going to justify this and get that extra point on the AP exam, this Nernst equation would be a valid, perfect, and honestly for me this one's actually a little bit easier to visualize, and E would be less than E0. Now the second one's going to be an explanation of what I talked about, how we said that if CR3 is greater than 1 and Ni is less than 1, then Q is going to be greater than 1. And when Q is greater than 1, that will decrease the magnitude of the cell potential. All right? So E would go down and become smaller. All right? So this one's more sort of qualitative sort of understanding of it. I always kind of prefer a quantitative. I like to see those numbers being crunched. Okay, so we are actually going to stop right there because this we would only be able to just dabble a little bit into this, but there's something called a concentration cell. So we'll be doing that tomorrow, talking about these concentration cells and then looking at our very last equation. So we'll be getting to that stuff. But we got to save something for the last day. So we are going to stop here today with just knowing how you can play around with the concentrations. And what we're going to learn tomorrow is you can actually use that change in concentration to make a battery. You can make a battery with the same metals. Some of you figured that out, ways of making stronger batteries. When we did this in our first year chemistry, you made one solution really salty and the other one not as salty. That actually can increase, if you do it right, can increase the cell potential. And some of you made a battery that was higher than the theory because of changing the concentrations. And that's what we're going to get into a little bit tomorrow, and then do some physics-like stuff with current and so on. Okay? All right. So that's it for today. Relax and enjoy your Wednesday, and tomorrow we will do the last lecture, parts 3 and 4. Okay? All right. Have a great day, and for me, a great evening. I'm going to go watch some basketball.